discussion round. And thanks a lot for the talk. It was really nice. So now it's time for the open discussion round, and we have here Dmitry Berenson from the University of Michigan, Wenzhen Yuan from the Carnegie Mellon University, Dinesh Manocha from the University of Maryland, Jeannette Bohg from Stanford University, and we also have Rika Antonova, that is an organizer of the workshop from Stanford University. And Rika will be mostly in charge of moderating this open discussion round, but I want to remind the audience to ask as many questions as possible, and we monitor both the question and answer here on Zoom and also the Slido channel. So please, Rika, you can take the floor.
All right. Thanks all for the talks. It was very interesting to listen, and I'm glad the audience was engaged asking questions too. So for the discussion round, we'll start with 2 questions that were suggested by the organizers, 2 topics, I guess, and then we'll also perhaps have a 3rd topic that we could pick out from the audience. So the audience, please feel free to suggest the topic to consider in the Slido Q&A. So the first one was simulation and transfer to reality. Can we leverage simulators for real world applications? So to start off, there are a number of simulators right now, right, that can model to various degrees of fidelity and stability and success deformable objects, like ByBullet, Mujoko, all have added support for that. They are available. SOFA, which is a more, I guess, simulator that is more focused on perhaps medical robotics, NVIDIA Flex, and the newly introduced SoftGym have kind of basic environments for dealing with ropes and a bit with cloth. Unity has also a few plugins like ObiCloth, perhaps there are others. So now in all of these things, there are, of course, severe limitations. And so I'm wondering if one of the things that we could start off is maybe a few people who have used simulation for their work. What is the top limitation that you would single out to say that, okay, this really impedes my ability to use a certain simulator, or this just impedes my ability to say that these simulators have a promise to be useful for real world applicability? Whoever wants to start first, whoever has been annoyed with a simulation of deformable objects the most.
This is Dinesh Manocha. Can I go first?
Yes.
Okay, great. So this is a very big question. Actually, so I have dealt with simulators in 2 different domains for the last 30 years. If you go to the engineering community or robotics, we want what we call physically very accurate simulators, FEM and high friction and quite a bit of that. But if you go to like the gaming and graphics, and you mentioned Unity and VR application, in that community, people have developed what they call plausible. They visually look okay, but many times they're not physically accurate. Now, in our community, like in my own case, we use GraphSpit because that was available, and it seems to work well. But the bigger question that in my mind, we don't have a good answer to it. We are doing sim to real, and we're doing all this synthetic data set or other kinds of learning methods. What's the level of fidelity we have? Can we, many times we use game like Unity simulators, or sometimes we use very expensive, very accurate simulators. There's a trade-off between the accuracy and running time. I don't think we have a generic answer. Can we get a Unity type approximate simulators are very accurate? And if you look at the learning papers, you're seeing people reporting results with both of them. But what's the level of simulation fidelity we need for learning is an open question. And it's also possible, maybe in one case of what network I use, this particular fidelity is okay. But for some other application like locomotion or some other robotic application, different fidelity is okay. So I think there's still a big open question for the community. That's my take on it.
Yeah, I'd like to follow up on that. So I agree with Dinesh that this question of accuracy and how the simulator is used is crucial. And the way I see it, there are kind of 2 ways of using simulation for the kind of work we do. One way is to run it in these massive kind of cloud computers or whatever, just generate tons and tons of simulations to learn some kind of general policy over let's say, rope or cloth or something like that. And another way to use simulation that's prevalent is to assume the simulator is basically a stand-in for the real world object, so that when I'm running my control or planning online for some given object, then I can just call my simulator to tell me how that object will move. And to me, these are two actually very different applications and make very different assumptions about the qualities of the simulator. In the massively kind of parallel, get a huge data set world, I would argue we don't need especially accurate simulators unless we're doing something very, very minute, and we have to be very careful about how we manipulate. We would just need kind of fairly accurate simulators that are very numerically stable. That's a huge issue. And also, we can tune the parameters to generate a bunch of different behaviors over different kinds of stiffnesses and so on with the object. Whereas online, I feel like we do not actually have simulation technology that can autonomously do system identification and accurate simulation for a real world deformable object. So for instance, simulating a cloth, many packages exist, but simulating this particular cloth that I'm wearing right now, I don't know anything that can look at this and do sysid and then have an accurate simulation.
So perhaps to go into this, how to do this particular object simulation, do you think there would be possibilities for doing something like real to sim? So if you have a simulator which is somewhat flexible, right? I think the differentiable simulation maybe comes in as a topic, but it doesn't have to be differentiable. It could be black box and we estimate its parameters with other methods. Would it be possible to perhaps develop a bit further the methods that would take a few hardware like observations of like the actual cloth or maybe like your robot trying to wiggle this cloth or stretch this cloth on hardware, and then put it into the simulator, turn a bit of the optimization, and then do something good with this? Do you think that's a possibility? How would we explore that?
So my response is, well, is it a possibility? Of course, yes, definitely. But there are reasons that's really, really hard to do. So when you go sim to real, you go from huge amounts of data to less amounts of data, right? So you're already pre-training on tons and tons of data. Now you can apply, maybe fine tune on a smaller amount. When you go real to sim, real means less data in robotics, unless you're Google and you have an ARM farm. It means you've got much less data, right? So you're trying to identify these parameters or whatever they may be of the deformable object from a small amount of data. And you can probably do that, but what I'm worried about is that the model that you fit to this data will only be valid given what you've shown it, and what you've shown it is very little. So unlike in simulation, where you can test over so many different conditions and get tons of data, you're not going to have that data in the real world. So your model has the danger of overfitting, and then as soon as you try to do something different, suddenly the model breaks down.
So let me add, Dmitry, I think you made a good point. This is a great talk, but sim to real and real to sim. So I feel the term sim to real has become more popular in the last 6-7 years. There's a huge activity on data sets because of machine learning. But I would say real to sim has been in the published community, again, with my graphics hat, I would say, people have been doing for 15 years because what we call data-driven simulation. There's a lot of like fluid effects, you want to simulate complex bubbles or some big waves. Folks had no good synthetic models even, and they would take a lot of captured data and generate synthetic animations from that. So, but they remember the end goal for the real to sim, that community was to generate some visually plausible result for gaming or VR experience. So I think at the end of the day, it really boils down to what your goal is. So there may not be one generic answer, but I would say real to sim, what we used to call in graphic data-driven simulation, is a pretty popular topic, and it's widely used in all the commercial products, actually.
Right, so very interesting points. And maybe, I don't know, Wenzhen, you unmuted, maybe you can also comment as you go on how we have, and whether we do have a potential for having sensor information being simulated. That is currently kind of not present at all for deformables in simulator.
Sure, so I would like to say something from this different perspective. I'm not a big user of simulation, but I'm trying to be a contributor to a simulation. So one thing my group is focusing on now is to build a simulation model for the gel size sensor we are using now. And we are publishing our first paper on this conference. So if you are interested, welcome to our presentation on the force and tactile sensing session. So of course, like this is only the first step of our simulation work. So we also have some recent work and we are continuously developing our simulator, but like the simulation model for the sensor. So, but our goal is to develop a model that you can use in your simulation environment, either Majoko or PyTorch or the PyBullet or some other environment that we hope you can use the simulated gel size sensors in your in that environment when your robot is interacting with different kind of deformable objects. Of course, in the near future, we also hope to generalize our model to other tactile sensors as well. So hopefully people will get a chance to play with different sensors to see that what happens if you use this sensor for your task, what happens if you use the other sensor for your task, or even what happens if you create a new tactile sensor which doesn't really exist. So whether that will help with your task. So I think it's very interesting to hear the discussion from Dinesh and Dmitry that, like you said, that it's a big challenge if this is very hard to match the models with the real model of the deformable objects. But my understanding is that like we can add lots of varieties on the objects used in simulation environment. But as far as we have good perception, we can quickly build a model based on the perception and the manipulation interactions. So probably we can come up with a good manipulation strategies on those objects. So here I'm trying to contribute and make a simulation model for tactile sensing that you can all play in simulators.
Can I ask a follow-up question, Wenzhen? So what are your thoughts on how close is it to the real sensor? Like, or if you're saying you are maybe simulating different kinds of haptic sensors, which one are hard and which ones are maybe easy to simulate, and which one has the smallest gap between sim to real? What is your thoughts there?
That's a good question. So currently our focus is with gel size sensors. So that is relatively a complicated tactile sensors in many sense, since like it has a soft surface. So the deformation or interaction between soft objects is very hard to simulate. So we're working on that, and frankly speaking, our current effort is kind of limited to the rigid object contact. So like if you're contacting some soft objects, such as like I showed in my presentation, like the example of pressing on a avocado and trying to estimate the hardness of the avocados. So I haven't really think a lot about that yet, since we don't have a good model of the soft objects overall. But for some like some objects is more similar to a rigid objects. For example, like one thing we have been trying to working on recently is cable manipulation. Like what happens if we ask a robot to grab some cable to insert or to do a routing or go through a hole. So the contact area is generally like a cylinder area, like the contact between the cable and the grippers. So for that part, as far as our big simulation environment has a good understanding about what's the geometry it is. So we can deal with the geometry pretty well, and the signal we get nowadays is already pretty close to the real sensors, real signals we get from the gel size sensors. But also we do have lots of challenge, like there have been lots of discussion in the sensor community that whether we can design more complicated sensors, sensors with more complicated structures, but hopefully could be smaller, can fit on a curved surface or smaller surface. So in those cases, actually there are more noise introduced in the sensor itself, and how to model the noise of those sensors could be a challenge. So on the other hand, so there are lots of more commonly used, I would say more traditional tactile sensors, which aim at detecting the normal force distribution with a spatial resolution of several millimeters. So I expect most of them are relatively easier to simulate for building the model. But yeah, we look forward to see how it works out.
So it could be also the problematic piece is that they are easier to simulate, but maybe they're less relevant for the highly deformable objects or central objects like cloth, right? So it's if you're estimating something that is deformable, like you were saying, avocado or sponge or something like this, where you still can feel forces, then that's good. And once you go into you really need to get into a certain configuration to feel forces, like you're holding on to two pieces of an object and stretching it to the limit, then maybe that's the only way that you can sense something, where it's just pressing on the cloth is not giving you anything. So I was wondering, maybe there's some, I don't know, alternative sensors in the sensor community that we don't yet know about that could be applicable and relatively easy to simulate. If you have comments on that, something that, I don't know, something that maybe we haven't, that hasn't been useful, let's say, for rigid objects, but could be an interesting thing for deformable objects and is also easy to model, if that something like this comes to mind.
I know that there's lots of simulation models for vision, so you can add a simulated camera, especially I know robotics people are very interested in the RGBD information for simulating point cloud. So I think that is a very important tool. So especially if we are considering clothes or cables, where the global information, global shape of the objects is very important. I think that could be very important, helpful. And also it represents majority categories of the perception tools used for deformable objects manipulation nowadays. So I think that is a good place to go. So other than that, I know that recently there are also some people thinking about seeing through tactile sensor, like the one developed also at CMU by Professor Chris Atkinson's group called finger vision. So the idea is that they want to combine touch with vision exactly on the fingertips. So their sensors can actually see through the finger, can see what is happened in front of the finger, and also can detect some of the contact information. So to many extents, this is very similar to the concept of proximity sensing. It's a kind of sensor can feel the objects before contact, but feel the object is very close to the sensor. So traditionally, people are trying to use infrared sensing or radars to detect objects close to the sensor, but also nowadays people propose to use vision. So I think the good thing is that with this kind of sensor for doing manipulation, you can get a finer information about the objects closer to the sensor, to the grippers, so that this is also possible to simulate in a way similar to the point cloud modeling.
Okay, yeah, that does sound quite promising. I was wondering, for perhaps people who are interested in the vision aspect of it, how far along do you think is the possibility of simulating RGBD data kind of for deformables? Because we're seeing sort of in this sim-to-real sort of world, a big rise of okay, now we have scalable, even kind of visually realistic worlds, right? And that is becoming a reality now, but can we have depth data? Can we have noise models that are reasonable for it? And what do you think about deformables? What is the potential there?
So let me explain. This is a very good question, RGB sensors. So I think one community that are looking a lot into this is now autonomous driving. The autonomous driving people, I saw some announcements, some work that Argo had done with, Deva Ramana's group. They're doing long range sensors. So I've seen a lot more work because there's a huge commercial impetus, there's a huge business model to support that sensor development, that they use mostly LiDARs and probably cameras. And also they use RGBD cameras. But in that community, I've seen some lot of good developments in those kind of simulators.
Yeah, we've had some experience simulating RGBD data for the purpose of sim to real. And the hardest thing to simulate are the real sensor noise weirdnesses of the Kinect, right? Everybody probably knows about the trails you get on the edges of objects and how specular properties of objects can disrupt the Kinect. That's hard to simulate, but there are some tools available for that. People have been working on that. I don't know the reference off of the top of my head, but I think we did end up using some published work that tried to model that kind of stuff for the Kinect, at least the sensor trails part.
Maybe
and that really did help.
code.
It wasn't. Was that?
Maybe you used my code.
Yeah, it could be Jeannette's code. I don't
the
remember.
one I re-implemented was Blender. It was like a Blender plugin, and that one had a pretty good, not the specularities, but just generally all the quirks from the Kinect sensor were kind of implemented there, and I just re-implemented it in C++. So I don't know. Maybe you use that.
Oh,
no
yeah,
support
sounds
anymore,
like
though.
it. Great.
But I would, yeah, sorry to interrupt. I would say actually, depth sensor is depth data. I don't know if you agree, Dmitry and others, is not such a big deal. I would say depth data, even if you're not capturing like all the quirks, it transfers much better to real world than RGB. RGB is much harder to do for the realistic and really well, yeah. I would say.
Yeah, I guess the way we were looking at it was, in our work, we basically treat things that are out of distribution with respect to the perception we've learned as the object is different, right? So if that out of distributionness is disrupted by the sensor quirks, then our kind of object is different detector, is going to turn on erroneously. So for us, we kind of treated RGBD just as, 4 channels, and we didn't really try to figure out which one was more or less reliable. But I would agree in general that depth data is a little bit more forgiving than RGB.
All right. Well, that sounds hopeful. Since also that maybe Jeannette, you had another comment.
Yeah, I have like just one follow-up question on your question. Actually, I would say this is the depth data that it's more forgiving. Is true for rigid or deformable object. Or Rika, were you thinking of something specific that makes it harder to simulate visual
maybe
deformable objects? Because I was thinking,
yes.
Like, is there a difference? I would say no,
yes.
but I'm not sure.
Right. There might not be a difference with everything, but I was thinking of some specific case. So for example, grasping rigid objects with a regular parallel gripper, right? The biggest problem we found is when we wanted to grasp everyday objects, if they're very thin, their perception gets into the noise of Kinect, right? And then we moved on to trying to deal with cloth, which if you spread it out, it is very thin, right? And at the point where that gets, all of your object basically gets into your sensor noise. Now that's a problem. So that's one case that I was thinking. So like, for example, for a piece of foam that keeps its shape, right? That's not a problem. If sort of the issues that arise are the same, right? But if the objects you're dealing with are very thin and get into the sensor noise a lot more often, then filtering out that noise would be a nightmare. So that's what I was thinking about here.
I see. You're thinking of these thin structures, like just wrinkles and stuff like this and folds and everything. Yeah. That makes sense. Yeah, that's true.
So that could be, yeah. All right, cool. So let's see. Now we can move on to actually segue into what is robust enough to deal with various problems, right? We had this second sort of topic direction on methods for evaluation. How can we compare different methods that are proposed? And having watched the IROS, I think it was last year, I think a few of the panelists here were participating there. There was this topic that arose about the benchmarks. And I think the consensus was kind of that it is hard to design a benchmark which would capture the richness, like a benchmark task that would capture all the richness that we want out of experimenting with deformable objects. We haven't yet defined like concretely what are like all the spectrum of problems. So some of the suggestions were something like maybe we could share a common set of objects. I think Dmitry was suggesting that, and kind of like have models of them and kind of like pay attention to them, but not define concrete tasks. And I think Wenzhen was pointing out that maybe we also kind of define more precisely what we mean by different types of deformability. And then Jeannette was saying it would be good to have common access maybe to a hardware platform that was similar, so that people can experiment on the similar hardware, but they could also still define their own tasks. So that was sort of the quick summary of the benchmarks or not to benchmark or not to benchmark. But I was thinking in terms of evaluation, can we step back a little bit and think about, well, why do we need the evaluation like in the first place? What is it that we're not actually like want to check mark on, did I beat everybody on this benchmark or not? What we want to find out is what are the methods that are useful and for what kinds of tasks, right? So in that vein, right, how can we evaluate, or even how can we like make sure that we can share the current methods that, let's say we present at the conferences, right, and communicate that they are ready to be used by other labs. Now, the difficulty with that is that we don't really have a concrete kind of taxonomy of what methods are applicable to what concrete situations for deformable objects. So basically, how do we handle that? So to pose this question for discussion is, how do we do evaluation in a sense that it's informative? So like which method would be applicable outside of the author's labs circle and on other hardware as a component in another system for another set of tasks? How do we communicate this? How do we evaluate this? How do we structure this?
Well, in some sense, what you're kind of driving at is the heart of the scientific replicability crisis, right? This is not just in robotics. This is in, I think started in psychology, but now in physics, results are not replicating, and it's a little bit of a crisis in the standards that we use to say something as a scientific contribution. And I think in robotics, it's much the same, right? I mean, you can define benchmarks and you can, create simulation benchmarks. I think there's a lot of value in that, but is it going to work on a slightly different simulation? We never know until we try. And that's kind of annoying in robotics, that we always have this issue that we don't know if it works until we actually try it. But on the other hand, we work in such a complex field where so many different factors are involved that, being able to actually generalize across any one of those factors is hard enough, but multiple factors simultaneously, like different robot, different material of the object, different stiffness of the object, it's a lot of axes to generalize over all at once. So maybe, I guess what my summary of my response is, we gotta set our standards lower, okay? Everybody wants to, just publish a paper now, all cloth folding is solved, all rope manipulation is solved. Guys, it's not gonna happen with one method. I'm sorry, it's not. So like, we just have to be a little bit more modest in what we're trying to do, and understand that we're not going to have like a thing that says this is guaranteed to work for my application. You're going to need to try it. It's better to try things that do well on benchmarks and have good theoretical properties than to try things that won't. Yes, but you're still going to need to try a few things, and you're probably going to need to develop on them.
Okay, I think that's useful suggestion in the sense also making more concrete and more explicit, like what sort of settings has this been already tried on, so that another lab could gauge themselves whether their setting is close enough. So that could be useful.
I guess one thing to list or to categorize work on is always just to look at the abstractions and representations that are used, right? So for example, I'm just going to pick one example from my own work, which is what I just showed, right? And there we use, we parameterize the actions to be end effector positions. So and now whatever arm you have at your lab, right, doesn't matter, because the only thing you want to do is to servo that trajectory of the end effector. Who cares about your kinematics? that's one thing. The other one is Dmitry is gonna respond to that. I saw it. The other thing is the sensors, right? Like, what's the input? Some papers just don't have these very clear input-output descriptions, right? And a list of abstractions. I think if you wanted to do something like that, like actually say, here's something you can use, and here's why, then the input, output, and representation would be useful. But yeah, Dmitry, what's your response to that?
Well, so I like abstractions too, and they're very important. Like you can't do anything without them. You know, to just, well, I mean, I guess you can do pixels to torque stuff, but that has its limits. So you were referring to the kinematics, and the reason I just jumped up on that is because we ran into exactly this problem. So initially, when we were doing some of the work I presented, we were just planning for the end effector positions of the robot, and it was holding a rope. And you know, you can kind of do this and move the rope around, and you're like, okay, cool. Now let's put it on the robot, and we'll just use IK to track those end effector positions. I mean, this
well, I didn't say you should use IK to track the end effector positions.
Well, so, okay, fair enough. But the problem was that what we found out when we put this on the real robot was that the end effector position actually did affect the thing we were doing, because sometimes the geometry of the gripper would kind of catch on the rope, or the rope could snag on it in certain orientations. Definitely the reachability of the robot has a huge impact on where you can and can't go. You know, we weren't working with heavy objects, but also the heavier the object is, that also constrains where in end effector space you can go, because the robot arm, the more outstretched it is, the more you know, torque is required. So again, I'm not trying to say we shouldn't use end effector positions. We still do that, but we just add more sauce to like.
Yeah, I mean, this was just an example, right? Like, let's say an end effector position that is the output of your method is easier than joint angles or joint torques, right? To transfer to other. It's not the, you know, the end of this question, but I would say it's better. The abstraction matters. That's all I wanted to say, and it was just an example. But if you wanted to facilitate this transfer to other labs, then just stating these things clearly would be good, I guess, which is what papers are supposed to do, right?
Yeah.
Right. Yeah, so that's a good point. Basically, maybe also explicitly kind of striving to make it a little bit more generic than it just needs to be for a paper, so that another lab that works with a different robot and has a different representation, but the high level representation can match, they can also benefit from it. All right, and I guess to close that, like, would it be useful to maintain some sort of categorization or like a summary of what are the different methods that are current, or you know, like from the older times, where is the code and all that? Or do you feel that the field is still kind of like, there are too many things going on, and at this point, it wouldn't be useful to even have a web page with all the links kind of to summarize this, or to try to categorize this. Not formally categorize this, but just say like, oh, I work with cloth. What are the things going on there? I want vision for cloth. I just wanted an off-the-shelf vision for cloth. Well, off the shelf in quotes, right? Because I work on something else. I work on whatever control or something like this. Do you think this would be useful? Can we set up something like this? Or do you think we should just like step back and wait a few more years?
I think this would be super useful. I'm just not sure how practically it's going to be handled, right? There has to be someone who's really motivated to keep this up to date and to test all these things somehow, right? And then there has to be this benchmark.
I wasn't thinking like testing. I was thinking just like listing, right? So like pointing at the paper results, or the, you know, the talk summary or something like this. Not really like we have tested it in our lab sort of thing. That would be a huge amount of effort.
Yeah. Okay, fine. Let's not use that. But yeah, I'm just wondering like who would do that, right? Like it's like someone, it must be a deformable object influencer or something like that, who lots of people follow. Yeah, I just don't know how, you know, how practically.
Right, this would be implemented. Okay, so I get the to-do is to find a deformable object influencer, and then after that point we could propose.
Yeah, you know, like I think what we're discussing about, it's all about incentives, right? Like it's all about setting up the right incentive structure. So for example, if there was some external incentive that gives you as a researcher in some way benefits for optimizing for your algorithm, porting to other labs, like as it is, then, then it would happen. But I feel like the incentive structure is not set up. The same with your suggestion, right? Like, what's the incentive of this influencer, right? Like to put in this work of keeping track of it, right? Fame, I don't know. Maybe there would be some companies who are sending samples of deformable objects. I don't know, so I think it's all about incentives.
Yeah,
they are not set up for this stuff.
Right. So we'll see. Maybe somebody with the right incentives arises. All right, so then to kind of close off, so we were saying we'll monitor Q&A from the audience to see if we have a third topic. We ran a little bit kind of over time from the previous scheduling, so we'll have kind of a short maybe summary. And I think one question that I see here in Q&A, which is kind of like more global, is saying, what are the main challenges and bottlenecks for achieving good performance in manipulation of deformable objects? So maybe just like very briefly, currently in what you have seen so far, what do you feel is either a bottleneck or like a great opportunity that maybe, people will start looking into more in the upcoming, I don't know, few years, just from your experience or from your perspective? Maybe each of the people on the panel could just have a brief note about that.
Maybe I can start. I mean, kind of everything is a bottleneck, right? But I would say choosing the right abstractions, like that question that Martina asked me, which I think it was from Martina, right? Like, okay, how do you represent all these different pieces of cloth and all of this in order to make it perceivable and then plannable and generalized and all of this? I think that's a big question. I think there's a lot of work to be done there. And then what I'm always interested in is this whole field of soft robotics. So if you have a robot that actually has a soft material or is made of soft material, how do you control and how does it do proprioception? Do you even need it, or to what extent do you need it? These are all very interesting questions and a little bit different from manipulating deformable objects with a robot, right? It's more about how do you control this robot itself. And the other thing I had something else. Oh, and the other thing I'm always seeing is like this, actually trying to real applications. Like I've seen a lot of work on assistive dressing and things like that, which are so hard. I mean, you have a deformable object, a human, and you have to dress it with something deformable. That's so hard. Yeah, I don't know. I find this at least a very challenging problem, but yeah.
I think we're all pondering now how to do it with a soft robot. All right, so then maybe, I don't know, yeah, Dmitry, maybe you have some.
Yeah, well, I just want to say, I don't know if participants can see the chat window, but I just posted a link to a survey that just came out about, what's going on in deformable objects. I just wanted to comment that it's interesting to, of course, keep a website and so on, but there has to be some effort to manage the flood of information, right? So these kinds of survey papers kind of package it up into like these kinds of people are doing this and that. That would have to be a continual effort, which is not easy. So I just wanted to mention that. In terms of bottlenecks, yeah, I agree with Jeannette. Everything is bad. I mean, not bad, but a bottleneck, right? We need better robots, we need better algorithms of perception, we need better control, we need better planning, we need better sensors. Everything is bad, right? But if I had to say, okay, well, what's really holding us back? I would have to say, I mean, obviously, you know best what you're working on, but it's the ability to generalize from small amounts of data with some kind of existing priors. We are not good at that, right? We really lack the algorithms to do that right now. And for the kinds of applications I look at, which are not so much in the factory domain, but more, somebody's home or whatever, we can't get lots of data for like some object that we just pick up. And so we have to use some kind of prior information and then a little bit of data to do things. And that's really hard. So I see that as a main bottleneck right now.
I think everything you said is great. I would probably say, given the graphics community actually spent a lot more on deformable simulation. And as I think Dmitry already mentioned, cloth. Cloth is something which is finally getting to be there. I myself work a lot of cloth. There's also a lot of work on things like smoke and fluids. So they're deformable objects, and then they're really deformable, highly deformable objects. There's probably much more work in the graphics community, especially data-driven simulation methods and a lot of validation. So I think the robotics community probably can benefit. Now, of course, the goals are different. Graphics get away with a little bit of visual simulation, but there's a lot more things they have done on data-driven simulation method, which I think robotics community can really benefit from there. Because if you can simulate highly deformable cloud, turbulent fluids, and very, very challenging situation, on the robotics, we can't even we can't do a good job holding a simple piece of cloth, and they're dealing with very high different cloth. So this kind of cross-pollination can really help us a lot, especially as we combine data, learning, and simulation all together.
Great, thanks for this positive kind of compliment to everything is a bottleneck sort of thing. All right, and Wenzhen?
I think what everyone said is very good. So I really understand we also have a big problem about how to generalize from a small data set. So this is actually connected to the other question. It's how to find the good representations of the data. So on the side of perception, so I'm really blessed to have this good system. We have good sensors. We have lots of information. We found that so there's no theoretical problems on the perception side at this moment. So, but finally, we want to build a robot system. We want to build a system that the robots can manipulate, can interact with those deformable objects. So what I work on is only one side of it is on the perception side. So finally, we need to connect this perception side with the entire robot system. So the question is, what this connection could be like? So I show you an example, like for the objects made of deformable materials. Probably the most important things you want to get on the perception side is how soft this object is. So that is only a single number. But if we are considering some more complicated objects like clothing, fabrics, so it has so much varieties in the properties of them. There are so many different ways to describe them. So what is a good way we use to describe this kind of material? How can we use the information from perception as part of this manipulation framework? So what's this interface should be like? So this is a question. Actually, I don't have answers. So I try different ways. I try supervised learning ways, like based on human perceptions, ask a human situation about how would you describe a fabric, and ask a human to label the fabrics based on that. Also, my colleagues try some more hardcore way, like send the fabrics to a mechanical labs where they do lots of mechanical tests on the fabrics. It's very costly, and also actually we don't really know whether it's really help better than human perception. Also, in another work I haven't got a chance to show today, we did some unsupervised learning. So it's only based on the perception side. We connect vision and touch information. We try to learn some shared descriptors that can be get either from vision and from touch, where we hope can describe some invariant description of the fabrics. Although we don't really know what it is, but we found that there are some similarities of the material itself regarding to this representation description. But that is not connected to the manipulation side, finally. So I think finally we hope the entire community can work together, can have more communication about what is the best representation, what kind of representation we really want to get from the perception side in order to make the entire system work well.
Yeah, that sounds like a very important point. If we wanted to have some modularity, right, and some labs or people would be experts in perception, exporting kind of their algorithm, if there's kind of a miscommunication on, well, what is the representation that this is able to handle, or the controller learning algorithms on the other side can't use it very effectively, right? Then this is a bottleneck, I guess. All right, great. So thank you very much for contributing your thoughts to this. And I hope that, yes, the community of, that's interested in deformable objects and manipulation and representation of them and so on keeps growing within robotics. So hopefully we'll see more of workshops like this in the future and maybe even conferences.
Before we close, I just wanted to highlight there was one more slide or question about adding deformable manipulation as a keyword. Similarly to getting a track dedicated to this. And this goes out to the more senior people if they are editors at some point, maybe push for that. This workshop was actually born of when we identified the need of finding papers about deformable manipulation, and in all kinds of tracks. And in this workshop, we try to kind of focus it a bit. So if you have the possibility to influence that a bit, I encourage you to use your power for the good of the deformable object community.
Well, we want to thank all the organizers. This is a lot of effort on your part. So thank you. It was a learning experience for us.
Yeah,
Oh.
thank you very much.
Yeah,
Thank you for being here. So I think we can close our workshop, and it was really a pleasure to have all of you. So really many thanks. And I want also to thank all the spotlight presenters and all the people that were here. And of course, I also want to thank the organizers, and I hope you enjoyed this workshop. I think it was really great, and your talks were really great. And so that's it. Thanks, everyone, and I hope we'll have another workshop like this. So I don't know if the other guys want to add something. And of course, thanks, Rika, for moderating this discussion round.
I want to say thank you so much for organizing this and keeping this going. The frequency of workshops on deformable object manipulation has increased a lot, and I think it's really driving a lot of research and interest in this community.
Let's hope it keeps catching on. Yeah, I think in that sense we can close the workshop. Thanks again to everyone, and yeah, have a good day.
Yep.
And I'm gonna end the session, and then we're gonna end the stream, and yeah, and hopefully see you guys around the conferences at some point in person again. In this spirit, take care and goodbye.
Bye, thanks.
Bye.